Okay, good morning. Today we will continue our second lecture. Now we'll invite Dr. Nuraini from Department of Mathematics. She will give a lecture about Introduction to Mathematical Modeling. Bu Nuning, please give your time, and I think time is 1 hour 30 minutes, maybe, and you start until at 11, and maybe we have spare 15 minutes for questions, answers, and discussions. Okay.
Okay.
Please,
yeah. Thank you, Pak Iqbal. Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. Let me share my screen. Can you see my screen?
Yes, I can see your screen, ma'am.
Okay, thank you. Okay. First of all, I would like to express my gratitude to organizer who invited me to talk in this international virtual course, Introduction to Astrophysical Modeling and Computation. But I humbly ask permission to change the title into Introduction to a Simple Mathematical Modeling and Computation. Different with Pak Hakim at the previous lecture, I just a beginner, so my keyword in my presentation is fun. So I hope you get a new perspective and also having fun with my lecture. And Pak Hakim much more fluent to speak English better than me. So English is not my mother tongue. So apologize me if I so many grammatical errors or words pronunciation. And please feel free to stop me anytime if you want to clarify something. So at first, I am Nuraini from Mathematics ITB. Who am I? I define myself as a person who likes to seek a problem in her life. So basically my competency is in mathematical biology modeling involving population dynamics, infectious disease modeling, some kind of those things. But Bu Hesti at all challenged me to speak in the sense of physical modeling. So once again, I have the permission to use a very trivial example for physicists or astronomer to use this modeling. And this is my agenda. First, about the mathematical modeling. What is mathematical modeling? Following by a simple case of example, and also comparison how about if we want to model kind of social or psychological problem. And then the last step I will leave as a discussion of what next to do list in your point of view. Then we go to the mathematical modeling. So as I said, I'm not fluent, so I just read this slide. Mathematical model is a well-defined mathematical object consisting of collection of variables, parameters, and rules governing their values. I mean, it needs a relationship between variables and also parameters. Models are created from assumptions. So the keyword, if you want to models, it should be a good assumption. So you can create your assumption inspired by observation of some real phenomena, in the hope that the model behavior resembles the real behavior, but kind of hard to do. And we have two terminology here in modeling, in a general science. Using data to obtain parameter value is curve fitting, not really modeling. And also using a computer to predict the behavior of some real scenario is also a simulation, not really modeling. Why? Because the model is assumed. And we involve underlying model and parameter determination, but for me, it's okay because the important things if we deal with the modeling equation, the first step, what is the question? We should declare our question and we try to answer that question. So no matter what, you can say this is also modeling, I think. And mathematical modeling basically is the process of constructing, testing, and improving mathematical models with some symbols, tools, and etc. And should be general in the sense of containing parameters that can be adjusted to strengthen, weaken, or modify the behavior of each process. And yeah, I see that they do not need to be general in the sense of working for all possible cases. There are so many little mathematical model that derive and be very general, involving like Newton law. And the success of mathematical model depends on how easily it can be used, and how accurately it predicts. This is very hard, and how well it's explained the phenomenon being studied. So the keyword is simplification. We start with the real world data, and we do some simplification. We put a very strict assumption. Then we go to the modeling process. Here we deal with variable parameters, relationship among them, and then we get some formulation. You can derive from the scratch. You can combine more than 2 equations, and so on and so forth. And then you use analysis in the sense of mathematical tools. Then you get a mathematical conclusion. Then you interpret the result as an explanation of your problem, or if you're lucky, you can get a prediction. And then you need a verification back to the real data. And you can do this kind of circulation as far as you need it. Then we go to the very basic step of make a model. Yeah, normally we model the change and a very basic equation that when we choose, it should be difference equations. So, for example, we want to explain about the future value. It could be affected by present value plus something changed, like behaviors, pattern, discrete time periods, and whatever. So the step, for example, if we have any data, we can plot the scattering plot of the data. We observe the pattern and describe the change in the mathematical terms. And how to accommodate the change if we want to see the behavior, for example, we can capture by some function that explain as a sequence. So when this delta comes to be a differential equation, difference can be changed to differential equation if we take delta to infinity. For example, if we want to incorporate the change over time, and if we take a limit time to delta t to infinity, then we have some kind of differential equation. And the rule to construct a model, this is not a strict step, but you can follow this step. First, identify the problem. We should understanding the problem. We make an abstraction of the problem, make some sharp question of the problem. Then following, choose a good assumption. Based on this assumption, we can make our model. And you know, perhaps a very famous quote from Josh Box, one of the mathematical modeler, just say that all models are wrong, but some are useful. Actually, I'm agree with him, because if we deal with model, we should rely in our assumption. So we can make a very complex phenomenon to just like formulation or simulation. But otherwise, we need very simple as possible. So yeah, we should deal with this assumption. To reduce complexity, to define a variable, parameter, and their relationship, and so we should choose which one is very important in our problem. So after make assumption, we also have a variable and also parameters. We can make a model. We deal with formulation. You can adopt existing formulation, or you can derive your own formulation. Don't forget, if you deal with some physics or astronomical situation, you deal with dimension. So that's very important. So after make a model, of course, we solve or verify the model and back. Is that answering your problem? And is that make sense? So if the answer is yes, so you need to implement the model. We should explain in the term of stakeholders. So I speak about in a general term. For example, decision makers or industrial problem, for example, in my field. So we should translate our equation to the very basis notation or yeah, narration. So if they use our model, so we need to maintain the model. We should check and extend the version if possible, and etc. Then this is one of the example modeling using proportionality. I cite some of my slides from first course in mathematical modeling by Giordano et al., 5th edition. Recall that if we have proportionality, for example, y proportional to x if and only if y equal to x times some constant positive. So other example of proportionality relationship, we can change y as a line to be x squared or x cubed or whatever, or ln x or exponential of x. Also, the transitivity rule for proportionality is also applied. For example, y proportionality to x and x proportionality to z, then y proportionality to z. And using this proportionality, we can have a geometric interpretation. For example, if we have relation between x and y in xy plane, we have y equal to kx. It means that the line with some angle theta, sorry, angle theta. And other examples, if we change the equation kx to be x cube or x square or ln x and exponential x, we will have a different kind of slope. It can be gentle or sharp, depend on our problem. And this is some famous proportionalities models, comes from physics, Hooke's law, Newton's laws, Einstein's theory of relativity, and I think the very connecting one with astronomer is should be Kepler's third law. So I think she will be better explain this Kepler, the harmonic law better than me. So let's check this video.
Kepler's first and second laws of planetary motion appeared in their earliest form in 1609 in the book Astronomia Nova. They state that 1. Planets move in elliptical orbits about the Sun, which sits at one focus. And 2. A planet's orbital velocity varies over the course of one revolution, such that a line drawn between the planet and the Sun will sweep out equal area in equal time, wherever in the orbit you are. Kepler published his third law 10 years later in his 1619 book Harmonices Mundi, or The Harmony of the World. By sifting through observations of how the planets move in their orbits, he noticed something curious. The time it takes for a planet to orbit the Sun once, its orbital period, p, is related to its average distance from the Sun, its semi-major axis, a, in a very specific way. The square of the period is proportional to the semi-major axis cubed. In fact, if we choose our units carefully with the period in years, the time it takes for Earth to go once around the Sun, and the semi-major axis in astronomical units, or AU, the distance between the Earth and the Sun, about 150 million kilometers, the proportionality becomes an exact equation. The square of the period is equal to the semi-major axis cubed. Let's try it out. Earth's semi-major axis is 1 AU, because that's the definition of an astronomical unit. Mars is farther from the Sun. It has a semi-major axis of 1.524 AU. We can use Kepler's third law to figure out how long it takes Mars to complete one orbit around the Sun. That is, how many Earth years make up one Mars year. The semi-major axis 1.524 AU cubed equals 3.54, and the square root of that gives us Mars' orbital period, 1.88 Earth years. Sure enough, Mars takes 687 Earth days to orbit the Sun, which is 1.88 Earth years. And this works for all of the planets in our solar system. But what if we don't want to use astronomical units and Earth years, but something more conventional, like kilometers? Then we have to unpack Kepler's equation a little bit more. In modern notation, it becomes p squared equals 4 pi squared over g, the gravitational constant, times m sun, all multiplied by a to the third power. That term before the a cubed is the constant of proportionality in Kepler's original equation. M sun is the mass of the Sun. And to be completely accurate, the equation should say m Sun plus m planet, the mass of the Sun and planet together. But because the Sun is so much more massive than even the biggest planet in our solar system, Jupiter, the mass of the Sun is more than 1,000 times the mass of Jupiter. The extra mass added by m planet is tiny compared to m Sun, and doesn't make much of a difference. G is the gravitational constant, which might look familiar if you've ever seen Newton's law of gravitation, which states that the force due to gravity equals G times big M times little m, all over the distance squared. Actually, you can derive Kepler's third law from Newton's law of gravitation, although, of course, Kepler didn't know that. By setting the force of gravity equal to the centripetal force, the force the planet feels because it's revolving around the Sun. Let's consider a circular orbit first, because that's the simplest case. The centripetal force depends on the planet's speed, v, which for a circular orbit is constant. F centripetal equals mv squared over r. Setting these two forces equal to each other gives us a relationship that simplifies to v equals the square root of g times m over r. Now, since we're considering a circular orbit at the moment, we also know that there's a relationship between the speed v and the orbital period p. The planet has to go around the whole circumference of the orbit, 2 pi r, in the time p, so the speed must be equal to 2 pi r over p. And if we substitute that into our force equation from before and use the semi-major axis a as our distance from the Sun, now we're back to elliptical orbits, we have 2 pi a over p equals the square root of g times m over a. After some rearranging, we've gotten back to Kepler's third law. That is, p squared equals 4 pi squared over g times m Sun, all multiplied by a cubed. This expression is especially informative because it relates two values that you can measure with a telescope: distance to the Sun and orbital period to the mass of the Sun. And that's how we know how heavy the Sun is. Even better, it works for all kinds of orbiting systems. You can find the mass of the Earth, for example, by rewriting the equation using the distance and orbital period of the Moon. The Moon's orbital period, p moon, is 27.3 days, or 2,358,720 seconds, and the semi-major axis of the Moon's orbit, a moon, is 384,400,000 meters. G, as usual, is 6.67 times 10 to the negative 11th meters cubed per kilogram per second squared. Solving the equation using these parameters yields an estimate for the mass of the Earth of 6 times 10 to the 24th kilograms. Any planet with a moon can easily be weighed this way, and it's all thanks to Kepler's third law.
Okay, so that's better. It's better to explain this kind of Kepler's third law rather than me. So although Kepler discovered what is now known, the three laws of planetary motion or harmonic laws, he could not explain why they were true. So that did not come until years later from Isaac Newton formulated the laws of motion that are still valid today. Newton formulated what is known as his second law of motion, that net force equal to mass times acceleration. Then this enabled him to formulate how objects are influenced. For example, the weight equal to mass times gravitational speed. And then he was also the first to identify the acceleration on objects forced to move in circle. So the keyword should be circular orbital. So this is, we have acceleration equal to the speed square or velocity square over distance. In our problem should be a semi-major axis. And therefore, we can substitute those acceleration to the force of C, and we get this equation. And finally, what is perhaps the greatest intellectual discovery of all time, the law of universal gravitation, that is force of G equal to big G as constant gravitational, and big M is mass of the sun, and M should be mass over R square as distance. And yeah, once again, although the orbits of the planets are ellipses, when we derive the equation, they are very close to circles. This is our assumption. So we can use rather easily to put everything when we assume the orbits of planets are circles. So we have those equation for centripetal force equal to the gravitational force, and we substitute all elements to this equation. We have speed square or velocity square equal to big G times big M over R. This is gravity provides the centripetal from of the satellite. And yeah, back to the circular orbits, the tangential velocity of the object is simply the circumference 2 pi r divided by period. So we have this one, and we substitute to the velocity equation, then voila, we have the third Kepler's of law. We have right hand side as a constant. So perhaps sometimes the researcher denote this as constants, K-sun. So this is a very simple equation, but a very deep insight of this kind of equation, and derived by the greatest science all of the time, Newton's and also Kepler. And based on this, if the distance of the planets to the sun are expressed in convenient units, like astronomical units, you know that 1 AU equal to the distance from the Earth to the sun, and the period is expressed in Earth years, then the constant K equals to 1. When we calculate this for our solar system, then yeah, K should be equal to, nearly equal to 1. And we can do this for all planets and also stars. And we move to the second case study, the light pollution. This is the result for our modeling, mathematical modeling group, Night Sky Glow, and work by these 5 girls, collaboration with Pak Dani and also Pak Khatib Kunjaya. What is light pollution? I mean, the overall brightening of the night sky by man-made lightning is defined as light pollution, not the glare caused by luminaries near the observer. And light pollution is a large-scale problem, I think, because a small town can light an area of several 100 square kilometers, and a difficult problem because officials who have lights installed feel completely justified in doing so. And the problem is complicated by public ignorance. So few people, including amateur astronomers, know what a natural night sky looks like, know what they are losing indeed in the case of light pollution, as distinguished from other kind of pollution of environment. And the society at large does not value what is being destroyed, I think. So the motivation, we want to modeling the relationship of the factors that affect the size of brightness of the sky. In example, population growth and distance from the city observation to the level of light pollution as contribution to science. Very small begin contribution to science that is expected to help in the field of astronomy. And there are three components that affect the light pollution: the rapid development of technology, increasing population, of course, and overuse of lights. And I'm worried that you are bored with me, so we have some videos. This is an example of light pollution. For me, it's a very touching video. The high level of light pollution. Okay, yeah, you can compare these two graphs in a figure 1. Light extinction comparison between low light pollution compared to the high level of light pollution. Different with the hot, spicy food that we want to eat. High level is means good, for example, for some of us. But in light pollution, if you have a high level of light pollution, that could be, yeah, not nice, I think. Yeah. And this is also an example of the growth population in USA from 1980 up to 2005. We can see the numbers of light comes from the earth that should be affect the sky brightness. And our exploration using 3 points of data. First in part of Bandung City, and then in West Bandung district, and also in Cimahi city. We compare 3 sky brightness data from 2011 up to 2016. We can see in the X line it be years, and in the Y line is light intensity in NPSAS. The first one, the red one, is for Bosca in Lembang. We have data from 2011 up to 2016, but like in 2014, in the middle, we have data for ITB. We have data for 2013 up to 2015, and the last, the blue one, is from Cimahi. We have 2011 and 2012 data, only 2 data. So if we plot in the XY plane, where X it should be years and Y is light intensity in MPSAS dimension. So we have the light blue is for Lembang, red is for ITB Ganesha, and yellow is for Cimahi. We call it in Bandung Raya areas. So the question, if we have data, but the view of data, we can do a statistical approach. So we should, before we choose our model, we should derive a question of this light pollution. We define 3 kinds of question. First, how does the observation distance from the city center affect the size of the sky brightness? And also, how does population growth affect the size of brightness of the sky? Can we model these questions? So it's a very linear question. We just see the factors of the distance, the source and the city center, and also the population growth in the 3 points of our observation data. And can we model this question? So our goal is to explain these 3 factors, these 2 factors in our model. So this is the data, measurement of sky brightness. I think astronomical surface brightness is commonly expressed among astronomers in terms of stellar brightness per unit area, and this unit is magnitude per square arc second. Is generally used in a small area photometry and measurement related to stellar physics, such as isophotometric of galaxies. The scale is logarithmic as all magnitude scale. The higher the MPSAS value, the darker the sky will be. So for example, if we have this West Bandung in years of 2018, we have intensity MPAS in 12, beginning with midnight, 00 midnight, until let's say 4 or 5 o'clock in the morning. I think 4, and then decrease up to 6 p.m. in the evening, then back increase up to nearly midnight. So we have a typical data for all the points. This source of data comes from Pak Dani et al. And we also have the population data for 3 points and for the consecutive years equal to the when the observation done, and also the distance from downtown city center, which is Cimahi for Observatorium Evergreen, West Bandung District for Observatorium Bosca, and ITB for Bandung City. And this is the distance for city centers, as we assume as a source of light. Then this is the height for 3 places in meters, Bandung, Cimahi, and West Bandung District. And, you know, Bosca is the highest place compared to others. And our modeling process begin with the engage with the problem. It is not easy because we should open our mind and studying others' competence. For example, this one, I should read the light pollution, the every dimension in astronomical point of view, and then discussion, read some papers, and etc. But this is our consequences as mathematical modelers. And second, we explore the information, the data, and we try to understand what is the data and so on and so forth. And then, yes, we choose a model. Unfortunately, in this presentation, I'm not elaborating the model, and also I cannot validate the result because we're still in this third steps of modeling. I choose a very simple modeling, and I think nowadays is also come up with the most high computation and yeah, and so on. Okay, like I said in the previous slide, if we deal with data, our first sense, it should be use a statistical approach using data sets. But unfortunately, it's only 3 point of place, and then we can insist using statistical approach. So we move to the second strategy using empirical modeling. So use physical approach using real phenomena, and our previous researcher that already observed this data. And we don't need any computational approach because it is still a linear problem. We're still in the first step of our simple modeling. So sometimes it is difficult or impossible to develop a mathematical model that explain a situation. It's also we deal with this light pollution, but data exists. So we can often use this data as the sole basis for an empirical model, which consists of a function that fits the data. And we want to, yeah, I think I can explain the effect of factors that already defined in the first place. So this is the empirical model that we use to our model. I said from Garstang, light pollution modeling, International Astronomical Journal Colloquium in 1991. Our first model comes from Walker's model. Walker's described the relationship for population and intensity of the light using measurements data from California. And light propagation law by trainers presented simplified models that estimate the contribution of aerosol scattering to the zenith brightness due to the light coming from nearby cities. The artificial zenith brightness was modeled by the population brightness function. We use a population, and the brightness distance functions of the surrounding cities. So we use distance in this case. And the sky brightness program based on trainers' work is developed by Berry, modified the brightness population function in agreement with the work of Normandin in 1974. I was born in 1974. They already make some kind of this hard empirical model in the province of Quebec to better fit the data obtained from Southern Ontario, and the last Garstang with a more complex model in 1984 or 1986. Then this is the Walker's model. You know, I is for intensity, P is for population, D is for distance, and C is for constants. Walker measured the distance from San Jose, at which the artificial brightening of the night sky at the zenith was 0.1 NPSES, and he combined this measurement with measurement at Mount Palomar, and with the assumption that the artificial brightening due to the city is proportional to its population. So the keyword, the variable is intensity versus populations. And in 1973, Walker revised this model, population distance relationship using better population estimates, although Walker did not mention it in his early papers. It is easy to show that his curve may be expressed to remarkable accuracy as P proportional to distance to the power of minus 2.5. So this is the Walker model. So sorry, our result is still in Bahasa because I have no time to change to English. But the Y line is the intensity of the light in MPSES, and the X line is for distance in kilometers. So the Walker's model result from for Bandung Raya data, intensity versus distance consistent for 3 places. That intensity is proportionality to 1 over distance square in this problem. Sorry, in this model. But when we explore to the data of intensity versus population, we found inconsistency for 3 places. For Bandung, represented by the ITB data, we have that intensity equal to population. And also for West Java district, represented by Observatorium Bosca, we have also intensity equal to the population, but not for Cimahi, for Evergreen Observatorium. Perhaps the lack of data will be taking place why we have inconsistent result in this case. Then this is Trainer's model. Trainers derive formula for scattering by aerosols. He considered a simple model consisting of a homogeneous atmosphere in which the relevant vertical heights are small in relation to horizontal distance between city and observatory. So similar with Walker's, trainers also deal with intensity and population as variables, and distance and others constant to be fit with the data available. And in trainers models, cities were treated as point sources when the formulae for contribution of single Rayleigh and double Rayleigh and aerosol, scattering all of those data are combined into a single formulation. The resulting expression is written to be as this one. So A, B, C is a constant, P is for population, X is for distance rather than D. We use X as our side from the trainer's model. And this is the result from the trainer's model. We have better result for intensity and versus distance. In this case, we have these parameters fitting based on the 3-point data in the previous. So we have only 3 points, and this function fit with this with those 3 points. And this is Barry's model. Barry used a modification of the model of trainer. Guided by his observation, he used the square root of the population instead of the population. So basically, Barry's model relied to the trainer's model, but he changed the equation of the population. We have population as a square root, and then he also replaced the distance g of the city with square root of d square plus h square. H is for height. So Barry also involved the height parameters in this model. Big A, big B, and also little a and k are constants, and it's depend on our data. Barry's model increased the importance of satellite cities relative to the main polluting cities in comparison with the model which assume that the light emission is proportional to the population. And this is result from Barry's model, not so different from our previous model. Same, we have I as intensity, P for population, X for distance, and other is constant. And this is our last empirical model, Gerstang. A major step towards a more complete model was proposed by Gerstang. And in Gerstang model, cities were not considered as point source, but as a circular uniform surfaces. The number of aerosol was adjustable parameters, and different scale heights for molecules and aerosol were established. So this is more complex model because there are extinction factors also involved, and double scattering correction also involved. I think comes from Rayleigh and aerosol, perhaps. Please correct me if I made mistake, Pak Dani, Pak Kun. And H stands for the head of 3 places. And this is result from Gerstang's model. And we also have a nice result. The 3 points are captured by this model. So in our first exploration of modeling light pollution, based on limited data points using Walker's model does not fit with one district, perhaps because the lack of data. Trainer's, Barry's, and Gerstang's model respectively show the best fit with all the data sets. It means that population increase affected the intensity of the dark sky glow. Kind of very trivial conclusion, right? But we're still in the first step of modeling process. So how high the level of light pollution occurs is actually what we want to answer. But in the result of this model, we have only come to see the relationship of light intensity to population and distance to the city center, which is seen as the largest light producers. And from direct observations and model calculation, there are observing sites of light pollution in Bandung Raya, which will degrade rapidly in the future. So the very simple modeling that we already done can have a warning to our decision maker to make some kind of regulation, for example, yeah, kind of those things. We hope we can have a contribution on that area. So that's the second case. Now we will move to the last part of our presentation, of my presentation, and I will take 3 minutes break. Please listen this music.
The Fibonacci sequence is a series of numbers where each number is the sum of the previous 2 numbers. The numbers in the sequence have extraordinary mathematical properties and can be found in patterns all throughout nature. So I decided to see what they would sound like as music. To create the melody, I assigned the numbers 1 through 8 to the E major scale on the keyboard and added 0 and 9 on each side with the natural extension of the scale. I played the resulting melody with my right hand and added harmonies with my left hand. Now, the first number of the Fibonacci sequence is 0, but 0 added to itself just equals 0 forever. In fact, that's what you've been hearing in the background. In order to start the sequence, we need to add a 1.
Okay, thank you. Why I put Fibonacci sequence in this slide? Because in the last case study, how about modeling in social science, I choose a psychological problem or some kind of qualitative information. So how to model qualitative information? Yeah, we just do some regular step. First, read, think, find a piece of information in data because we deal with the qualitative information. Second, back to assumption, define variables and parameters. And the third, normally, I present something that already done. So it looks so easy, but our struggling is in the second and the third place. What is our assumption? How we struggling with some kind of abstracting the problem and then choose the model. Is that too simple? Is that interesting or some kind of information? So before I go to our problem, I take from this website, pattern recognition in computational thinking. There are common ways we see patterns. Mathematics is a language of pattern. Patterns are the laws of nature and life that present themselves in all disciplines of life, from the smallest microorganism to microcosms. While patterns are always apparent, they are continuous and autonomous. So I like these examples how to the character design. We can we can distinguish which princess, prince, and god from their head. Human plus head, you can know which one is which, princess, prince, and god. So yeah, that's the clue. And what is this topic about? You know, the Asian, Black, Caucasian, and etc. This is a very linear example, but I like so much this kind of modeling, and I think I oftenly use this equation to introduce a modeling process in a very simple way. And what is it? Attractiveness. Here, so we have Asian, Black, and Caucasian face, and this is Marquardt beauty of marks. How would you quantify the 1 up to 10 attractiveness scale in words? This is our assumption. So you can argue me with you cannot define a beauty. This is very a broad definition, but yeah, we are modeler. We need some kind of quantifying something. Although this is a very relative, but we can use this. This is Marquardt beauty marks. The original face in my left hand, and the peer beauty marks in the right hand. Perhaps in the sense of our eyes, yeah, our naked eyes, we can see that the one in the right is better than one in the left, relatively better. Why? Because of golden ratio. So the vertical facial dimension, the distance from the eyes to the lip in the relation to the hairline to chin with a ratio of 36%. This is our golden ratio, considered the most attractive. You know, for beautiful lady, here's the line, the yellow line, landing in the right place, where should be in the eyes and the nose and the lip and etc. It will be different if I put my picture on that things. So very extremely, perhaps we have error placing the line. Yeah, but no worry, because the human face conforms most closely to pi proportion when we smile. So why we are happy when we see our family smile, our friends smile? Because the golden ratio, you'll be perceived as more beautiful with a warm smile than with a cold-hearted look of anger, arrogance, or contempt. So I think this very different topic with astronomical unit, but I hope you can accept this as fun things for mathematical modeling. So our previous slide inspired us to modeling beauty, beauty from a geometrical perspective. This is also a result of our modeling groups, and we exploring the golden ratio to geometrical object. So in the short line, I am not describe how hard we are to choose the proper model, but we explore the geometrical object based on its golden ratio. So the first thing, we survey the model. For example, a picture, a two-dimensional picture, we put some geometrical what is it? C-cell geometrical that fulfill the golden ratio using Fibonacci sequence, and this is hard. We try to find any triangle that fulfill the golden ratio, but we can generate the model. We place the star. Okay, this does not work. Any tetrahedron, hexahedron, or whatever, heart, and we insist the peer Marquardt beauty of marks. So it is not easy to plot all of these things here. We are not a plastic surgery doctor, so yeah, fail of all the survey. And we try to make more light using line, using ellipse, and nope. And finally, we choose isosceles triangle. An isosceles triangle with the ratio of the longer side to the shorter side meets the golden ratio. So we choose this one. So we can put these isosceles triangles with 22 degree as the golden ratio. So we have 72 degrees for both sides, and then 36 degree in the chin. So when we apply to this Hollywood star, it meets there around 72, but not really 72. And also to these pictures. And step 1, we collect all of the students' pictures. 1 in the normal behavior, 2nd with a smile. But unfortunately, not of all them have a warm smile. So that's also affect the calculation, I think. So step 1, a photo survey of all of the friends in 1 years, and then 52, I think, 52 picture. And step 2, calculate the angle. So for example, these students normal in right angle, he had 73.73, and the left he had 71.73. But when he smiled, it is not. I think that's not have any difference, yeah. But yeah, it meets 72.78. And the second students, when she doesn't smile, she not meet the 72 degrees. But when smile, yeah, meet both left and right meet 72 degrees. And they also do the same things. The girl in this slide also meet 72 degrees, but not at the top side, because yeah, I don't know what can we define with this kind of smile. And also me, I have no hope, normal or smile, this is still far away from 72 degrees. Yeah. Sorry, I should put my battery on. Okay, now back. After we collect all of the data, we use a statistical approach. We collecting the data for each picture, the angle between normal and smile mode, and we have this kind of result that the average angle of the smiling picture is nearly 72 degrees compared to the normal one. So yeah, you can see that this median, mean, and also modus and for smile picture is nearly 72 degrees compared to the normal picture. So this is an example of how to quantify any qualitative behavior to be give more scientific backup information when we want to explain some kind of psychological or social science. I don't know. There are a very generic situation, but we can do this kind of fun to deliver or to derive our model. So perhaps you can make your own picture with the 2D dimensional, no beautify, and then you can compare your normal face with your smiling face, and then you put a triangle on your graph and calculate the angle. And is that meet the conclusion or not? Or like me, I have no hope while I'm normal or smile. Yeah, still far away for 72 degrees. But yeah, nothing. And nearly at the end of my presentation, insofar as theories of mathematics speak about reality, they are not certain, and insofar as they are certain, they do not speak about reality. And I cite from Albert Einstein, and 100% I agree with this statement. And I leave a discussion as a conclusion. Do your own step to-do list if you deal with a mathematical modeling process. And I think pattern recognition for astronomical data are very useful and very powerful tools, as Pak Hakim explained in the previous talk, a very nice high computation part. But I'm just a simple mathematical modeler. So thank you very much for your time. I will back to Pak Iqbal.
Okay, thank you, Bu Nuning. We give applause to Bu Nuning for very nice lecture. Okay, yeah. Now open the question. Any questions from this room?
Perhaps too
Or,
trivial.
Yeah. Any more question? From Zoom? Yes, from Subham, please.
Hi, yeah, thank you for the wonderful lecture first. Okay, so when you showed the empirical formulas for the fittings of night light, right? So those empirical formulas were derived from the fitting, or they derived analytically and then fitted it to the data?
You mean our 3 points that displayed in the slide? Sorry, I can hear nothing from here. No, I think the noise is coming.
I'm audible now?
Yes. Okay.
Yes.
Okay. So you showed different models for modeling the night light, right?
Okay.
Berries and walkers. So those models were generated, like as you said, those are empirical models, empirical formula. So those were calculated by analytically, like they solved analytically and generated these formulas, or those are from the fitting, like from the fitting they got those models.
I think combine both of the approach, because trainers using some kind of position, the observer, the city center, and also the zenith, and he derived some kind of formulation in physics using angle, etc. And then he put the equation as in my previous slide, and then he tried to fitting those kind of formulation in his data in, I don't know, Quebec, Ontario, South Ontario, and then fit with that model. So I just adopt his model to our 3-point data. Is that answer your question?
Yes, yes.
Yeah. Thank you, Subham.
Thank you.
Okay. Okay, thank you, Subham. Is there any more question?
I think it's too trivial to answer, yeah?
No.
Is there any
Yeah.
comment?
Maybe I will also have a question for Nuning. I'm interested in the, from the pictures you make some modeling from triangle or about golden ratio. Yeah, in astronomy we have how to measure the morphology of a galaxy. It is a different type of spiral and elliptical. Can we use this type of a golden ratio as or just maybe a simple triangle or isosceles triangles with different type of data, different type of pictures, and something like that? Is it possible to, we can make different like a triangle or the golden ratio or circle or and how we test this type of picture using different like a golden ratio or triangle. How to test that? Which one is the best one?
Okay.
To simulate?
Okay. If I may not mistake for your question, Pak Iqbal, if you want to derive a morphological concept for example, a set of stars or whatever, the question is find the morphological geometry, I think. Is that correct?
Yeah.
This is the different question that we should ask rather than my example, because in my example, the question is we already define beauty, so we know how to see something using golden ratio. So the golden ratio is some kind of ratio that we can use to design something in the proportion of beauty. So for example, a graph, a face, logo, whatever. So different with your question, if we want to see or explore a morphological some like a star set or whatever, if the question will be leading to the some kind of beauty, yes, you can use this approach. But if you want to define a very specific morphology, I think it could be different with my approach in the previous slide. Is it answer your question, Paipa? Yeah. Yeah. I just answer your question as or I can leave to other astronomical astronomer insight. Yeah. Is there any other question? I cannot hear you, Baikbal. You say something?
Yeah, sorry, it's turned off.
Oh, okay.
Yeah.
Yeah.
Yeah. No question? Okay. Yeah. Yeah, this is very tough one in using make a model for astrophysicals, because first you have to define the mathematical part. This is the, and then like before Pak Hakim said, and then change it to transform it to the programming from the mathematical modeling and data, and then combine to the with data, and then complete using the computer programs. Okay. Yes, I think no more questions. We can stop here. Before Dr. Nuning, we will have some picture photo session. Please, all participants, open your camera, and we'll di ini aja. Ini aja, ke sana aja. All, yeah. Yeah, we will. This is our classroom. Okay. We'll take the picture.
Okay, please open your camera.
We will wait.
Okay, I will take for first page. 1, 2, 3.
Dari sini dada-dada.
Okay, again. 1, 2, 3. For second page. 1, 2, 3. Last page. 1, 2, 3. Okay, thank you.
Okay, finish. Okay. Thank you very much, Ibu Nuning, and for the very nice lecture. And before, can you your slides can be given to
Yes.
all the students here?
Yes, I will upload my slide in the previous link that Buluki already sent.
Okay. Yes. Thank you very much.
Okay, thank you very much. Bye bye. Bu Hesti.